Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So we will be going over the concepts discussed in week 5 and then we'll move on to week 6 concepts. So week 5 we studied directional and lateral stability control. So directional stability control, the conventions are right wing back, who is considered a positive yawing moment, and the positive beta angle, positive side slip angle was considered when the velocity vector is on the right. So if your aircraft, this is your fuselage, and if this is the fuselage reference line, if the relative velocity vector is on the right, this is considered positive beta. Similarly, the convention for rudder is rudder deflected to the left. So if your rudder is here, it's deflected to the left. This is considered positive rudder deflection. What this does is it generates a positive yaw. Okay, so it generates a force in this direction, which generates positive yaw. Okay, yaw is left, not a positive yaw, it yaw is left. Now for static directional stability, what we need is a restoring moment. So when the aircraft encounters a positive side slip angle, you need a restoring moment Cn such that the disturbance is removed. So for that, we need a positive yaw. So with an induced positive side slip angle, we need a positive yaw to counter it. The restoring moment is positive yaw, and hence the derivative Cn beta is positive. Cn beta is greater than 0. Similarly, this positive beta produces a force in the negative y direction. So here the rudder force produces a force in this direction. So your convention is positive y-axis, but the force is produced in the negative direction. Hence, Fy is negative for a positive beta angle. So this term, this force is negative. When we use that in the control moment, you need to put a negative sign to ensure that the entire term is positive, because this is negative, right? So it produces a positive beta produces a negative force. So this term is negative. Hence, you need to put a negative sign to make the entire term positive. Okay, so this is the expression for Cn beta. The components of the aircraft that contribute towards static directional stability are a vertical tail and a swept wing, both of which have Cn beta positive. So we studied here that Cn beta positive is what is required for static directional stability. And these are the two components of the aircraft that contribute towards positive static directional stability. Okay, positive Cn beta. Now for, okay, this is again side. So direction. So we study that a positive rudder deflection is the rudder deflection towards right, towards the left. This produces a negative moment. So what we can see that control derivative Cn delta R is negative. So for a positive rudder deflection, the moment produced, the yawing moment, is negative. Hence Cn delta R is negative. Now similar to the pitching moment case, pitching stability case, you have a tau, which is control surface effectiveness parameter. In this case, the control surface is the rudder. So you have dou beta by dou delta R. There you had dou alpha t by dou delta E, where elevator was the control surface. These are the equations for pitching moment, yawing moment, and the value that we discussed here, control moment coefficient, the derivative of control surface deflection. So this term has to be negative. It is negative, we can see, because this Cy beta, that is the force produced for a positive side slip angle, is negative. We've seen this previously. All of the terms are positive, hence this entire Cn delta R is negative. This table is just a comparison between the various terms used in the longitudinal and lateral stability control. So for static stability in the longitudinal case, you needed Cm alpha negative. So your graph was Cm versus either Cl or alpha. It had a negative slope. In the case of lateral stability, again, it should be directional. I'm sorry about that. In the directional case, the Cn beta should be positive. For trim, we required to trim the aircraft at a positive angle of attack. We needed Cm naught to be positive. There is no such requirement in the directional case, as usually it's trimmed at beta equal to 0. So your Cn naught is 0. So when you come to the control, your Cm delta E is negative. So for a positive deflection of elevator, you generated a negative moment. Similarly, for a positive deflection of the rudder, it generates a negative yawing moment. So these two are similar. Now moving on to the lateral stability control. So again, conventions were right wing down was considered positive roll. So for an aircraft, right wing down, left wing up is considered positive roll. So you're rolling towards the right. So what does that? Right aileron up and left aileron down. This is what ensures that you roll towards the right. This is considered the positive rolling moment. Okay. So rolling towards the right is positive rolling moment. Now for static lateral stability, what do you need for a positive roll? You need the rolling moment to be negative. Okay. So when it rolls towards the right, the restoring moment should be to the left, right? So your CL should be negative. Now, when it bangs to the right, that is when it rolls to the right, it bangs, right? It bangs to the right. We saw that a negative Fy is produced because a positive side slip angle is produced. When you roll towards the right, when the aircraft rolls towards the right, it encounters a positive. This is the top view, this is the front view, okay? It encounters a positive beta. This positive beta produces a negative force on the aircraft, on the rudder, which produces a negative rolling moment. So this is stabilizing, right? CL beta less than 0 is what is required for a conventional aircraft. And this again, so the Fy force is produced on the vertical tail, which is placed above the fuselage. Hence, it produces a restoring rolling moment. If this vertical tail were to be placed below the fuselage, it would produce the reverse moment, which is not stabilizing. Okay, this is why this is one of the reasons why vertical tail is placed above the fuselage. Now, expression for CL beta, similar to the previous case, is given here. We know that it should be less than 0. It is less than 0 because CY beta is less than 0. All the other terms are positive. Now, the components of the aircraft that contribute towards lateral static stability is a vertical tail, high wing, and low wing with dihedral. So, high wing has already a stabilizing component. Low wing has the reverse. It does not have a stabilizing component with respect to lateral stability. But if you introduce a dihedral on the low wing, dihedral is this angle. So originally your low wing was like this. When you introduce a dihedral angle here, it contributes towards lateral static stability. Okay, so it makes the CL beta 0, this dihedral. Low wing as such does not have CL beta less than 0. It has a CL beta greater than 0. So this is CL beta less than 0. This is CL beta greater than 0. Okay. Moving on to the questions of week 5 assignment. During a flight, if the aileron is deflected with a certain positive angle, how will this affect the directional stability of an aircraft? You're deflecting a control surface. How will it affect the stability? Come, let's talk about the pitching moment case, the longitudinal stability. Deflection of elevator, how does it affect the pitching moment? How does it affect the pitching stability, that is the longitudinal stability? Delta E, how does it affect longitudinal stability? Deflection of elevator, does it increase or decrease the longitudinal stability? In the longitudinal case, the control surface is elevator, right? So if you deflect the elevator, delta E, how does it affect the stability, longitudinal stability? Does it have any effect, or like does it increase, decrease? What does it do? For a positive delta E, what is the stability? How does the stability of the aircraft change? Can someone tell me? So stability of longitudinal stability, the parameter was Cm alpha, right? Cm alpha is dCm by d alpha, which should be less than 0. This is for a static longitudinal stability. Now, when you deflect the elevator down, how does this term change? Can someone tell me? Deflecting the elevator down is a positive delta E. So does the Cm alpha change?
It will not change.
It will not change, correct. It will not change because the control surface has no effect on the stability. It just plays with the control of the aircraft. It does not change the stability. Okay, so we remember that the purpose of control, like if this was your Cm versus CL graph, the delta E deflection just changes this, translates the graph to a different location. It does not play with dCm by dCl, which is an indication of stability. Delta E deflection does not change dCm by dCl, does not change dCm by d alpha, right? It only changes, it only translates the graph. So you are unable to trim at a different CL. That is the only thing that this delta E does. Similarly, in the directional case, if you deflect the aileron, positive or negative, doesn't matter. It will not have any effect on the directional stability. Okay, deflection of control surfaces do not have any effect on stability. So it remains unchanged. Contribution of vertical tail to directional stability depends upon. What does it depend upon? Does it depend on vertical tail volume ratio, vertical tail efficiency factor, or both of them, or none of these? So we know the formula. So this is the parameter that judges the stability, right? Directional stability. So what are the terms involved in this equation? You have a vertical tail efficiency factor, vertical tail volume ratio, Cy beta, the derivative of force with respect to the slope of Cm alpha will change if we want to change CL. Okay, let me go back to that. So this is your Cm versus CL graph for an aircraft, and this is the CL trim. Now, if we want to trim at a different CL, so if we want to trim at a higher CL, that is at a lower speed, suppose you want to trim it here, what do? You deflect the elevator, which essentially moves the graph such. It does not change the slope, right? Do you remember this? When we change the control surface, when we deflect the control surface of the elevator, it just translates the graph. It does not rotate the graph as such, right? It does not change the slope. This enables you to trim at a different delta E, a different CL, right? CL trim new. When I say change CL, I mean change the CL trim, not change CL. Okay, is that clear? What was the next question? Yeah. So the terms involved in this directional stability were the tail, vertical tail efficiency factor, vertical tail volume ratio, Cy beta. And this is a term that is analogous to the downwash in the pitching moment case. So these are the terms that contribute towards directional stability, where this tail volume ratio is further split into these things, where SV is the area of the vertical tail, S is, we know, the area of the wing, LV is the moment arm of the vertical tail with respect to the CG, B is the span. Okay, so these are the terms that contribute towards directional stability. From the options that are given, you have vertical tail volume ratio, that is VV, vertical tail efficiency factor. Both of these contribute, so this is the right option. Okay. Aileron control effectiveness depends on lift curve slope of the wing, lift curve slope of the vertical tail, lift curve slope of the horizontal tail, none of these. Now, aileron control surface effectiveness. So aileron is a control surface located where? Aileron is located on the wing, right? So your wing cross section is this airfoil, and there is a control surface located on it. So we assume that the lift curve slope of the entire wing and of this small section, which is the aileron cross section, are the same. So CL alpha wing is the CL alpha lift curve slope of this aileron. Now, how much? So what is aileron control effectiveness? How much lift it produces for a deflection? When you deflect the aileron down, what is the delta L? Right? How much lift, how much additional lift does it produce? Now that depends on what? It depends on your CL alpha. So your CL was CL naught plus CL alpha into alpha, right? So it depends on CL alpha. CL alpha is the CL alpha of the wing. So the effectiveness control, aileron control effectiveness depends on the lift curve slope of the wing. That is how much lift is produced when you deflect the aileron. It depends on the lift curve slope of the aileron, which is the lift curve slope of the wing. Okay. The primary control for adverse yaw recovery. What was adverse yaw? Can someone remind me what was adverse yaw? For yaw control, we know it is rudder. What is adverse yaw? So if you have an aircraft like this, it is the fuselage, and you have your rudder here, and this is the yawing motion. This is the positive yawing motion. So the control surface that controls yaw is rudder. What is adverse yaw? Can someone remind me what is adverse yaw? Movement in the opposite direction to roll. Okay, so adverse yaw is, it's somewhat correct. Adverse yaw is the yaw that is produced due to roll. So the rolling motion and the yawing motion are coupled. You cannot roll without a yaw. Okay, so the yaw that is produced due to the roll is the adverse yaw. Okay, and to control that, if you do not want it to yaw during such a situation, you use your yaw control surface, that is rudder. Okay, so that is the correct answer. For a conventional aircraft, the sign of CL delta A and CN beta are respectively what? Now, CN beta is a control derivative, right? So for a positive beta, we saw that a negative Cn is produced, right? For a positive side slip, you have a negative yawing moment. So your Cn beta, you have dCn by beta is less than 0. For a positive beta, your Cn is less than 0. So it's negative. Similarly, for delta A, this is not this similar kind of thing. So for a positive delta A deflection, positive delta A, positive aileron deflection was what? Right wing down was positive, right? Right wing down was positive CL, right? Right. Okay. So when you deflect your aileron positively, which is it rolls to the right. Okay. How do you make it roll to the right? You increase the lift on the left wing and you decrease the lift on the right wing. How do you do that? You deflect the aileron downwards on the left wing and upwards on the right wing. So left wing, right wing, you have downward delta A, and here you have upward delta A. Here the lift increases, here the lift decreases, and you end up rolling to the right, which produces positive CL. Okay, so this is considered positive delta A and it produces a positive CL. So CL delta A is also positive, right? Cn beta is positive, CL delta A is negative. Okay. Which placement of wing has least lateral stability? We just discussed this when we were discussing lateral stability. So if you have a high wing, you have a high wing configuration, right? And you are to roll it. So you roll it here. So the oncoming, this is the front view. Okay, so the oncoming wind, that is, it produces a side slip angle, it produces beta. The oncoming wind pushes this one and it produces a restoring moment. So this is stable. Similarly, if you have a low wing, and it rolls similarly, the oncoming wind pushes here. So it pushes here and it produces an adverse rolling moment, right? It doesn't produce a restoring moment. So this is not stable. Not stabilizing. Okay, you can't say not stable. Not stabilizing. This is stabilizing. So high wing is stabilizing. Low wing is least stabilizing with respect to lateral stability. Okay, so the answer would be low wing. Least stabilizing is low wing. Next question. This is the question that came up even on the forum. This was marked wrong, I believe. Let's just solve this nevertheless. An aircraft is flying in the south direction at a velocity of 50 meters per second under crosswind from west to east. So the aircraft is flying in the south direction. So the oncoming wind is in this direction. Aircraft is flying in this direction. So your velocity is here. So this is given as 50 meters per second. And there is a crosswind from west to east, which is 3 meters per second. So west. So this is your south, north, east, and west. So west to east is your crosswind, which is 3 meters per second. What would your resultant velocity be? This, right? So this is your beta. And since your resultant velocity with respect to this is on the right, with respect to your forward velocity, with respect to the fuselage reference line is on the right, your beta would be positive. This was what was pointed out as a mistake. So your beta in this case would be tan inverse of 3 by 50, right? What would the value be? Can someone tell me? I think it was 3.433 and it was marked wrongly in the assignment. It will be taken care of. Okay, so this is the correct answer. It is a positive beta. Since your resultant velocity, so let me just represent as VR. So resultant velocity is towards the right of your fuselage reference line. Okay, towards the right of the forward motion. In the forward motion, it says it's traveling south direction. Forward motion is this way. This is the aircraft. Okay. Similar to the previous question, along the same lines, so you have a aircraft flying in the south direction with a velocity of 60. And the crosswind similar from west to east, 6 meters per second. they've asked you to find the rudder deflection. Okay, so you have velocity. The answer would be positive. Okay, it would be positive 3.433 because your resultant velocity is towards the right of this, not towards our right, towards the right of your forward motion. Yes, is that clear? So if the resultant velocity is towards the right of the forward motion, towards the right of the fuselage reference line, the beta side slip would be negative. So if you were traveling towards the north, your oncoming wind would be like this. If your resultant velocity is here, this was considered positive. Similarly, if it's traveling towards the south, this is considered positive. Okay, so it would be positive 3.433. Is that clear? You just have to check if your resultant velocity is towards the right of the forward motion. Forward motion is in this direction, and this is towards the right of that. You can just rotate this image and see, this is positive, we know. Just rotate it, it comes similar to this. Okay. Okay, I'm moving ahead. So we were doing a similar case here. So your velocity is, the aircraft is traveling in the south direction. So your velocity is in this direction, that is given as 60 meters per second. And it is subject to a crosswind similar to the previous case, west to east, which is 6 meters per second. So now how do you calculate beta? This is again positive beta. Right? Positive beta. So beta is tan inverse of the crosswind 660. This would be, what would the value be? Tan inverse of 6 by 60. 5.7. Okay. Now they've given you the control derivatives, Cn beta, Cn delta R, stability derivative and control derivative. And they've asked you to find out the rudder deflection. What is the formula? How do you find out this? So we know Cn is equal to Cn delta R into delta R plus Cn beta into beta. Okay, so we've calculated beta, we know Cn beta, we know Cn delta R. At trim, the value at trim, how much rudder deflection do you have to trim? So this would be equated to 0. How do you, then you can find out rudder deflection? Delta R is equal to minus Cn beta by Cn delta R into beta. So what would the value be? Cn beta is 0.015, that is in per degrees. Your Cn delta R is also in per degrees, so no need to convert anything into beta. We've calculated beta also in degrees, okay? 5.71. What would the value be? What is the final answer? It would be a positive quantity because both the negative signs get cancelled. 0.015 divided by 0.009 into 5.71 comes to 9.516. Which is, okay. These are the formulas that we have used. V is the crosswind velocity and capital V, this was a small v, this is capital V. Capital V was the forward velocity. And this is the formula that we used to at trim, okay? At trim. Delta R required at trim. Now moving on to the week 6 contents. So we began again with the stability, the longitudinal stability. So this was the equation for the pitching moment, Cm naught and dCm by d alpha. For stability, we know that dCm by d alpha, Cm alpha should be less than 0. Cm naught is just the condition to ensure that you can trim your aircraft at a positive angle of attack. Now neutral point is described as the location, CG location at which Cm alpha is 0. Cm alpha is dCm by d alpha or dCm by dCl. Okay. So a neutral point is the location at which, the CG location at which dCm by dCl is 0. The equation we know, it was found as this. Without the fuselage contribution, this is the equation for the neutral point. This is stick fixed neutral point. The static margin is defined as such, which is the negative of the slope of dCm upon dCl. dCm upon dCl is this. Okay. Now, then we introduced the control parameters. Control was what? Like we had discussed in the beginning of this tutorial, to trim the aircraft at a different CL. So control surfaces were to ensure that you can trim the aircraft at different CL. So if you had to trim at a different CL, we just translated the graph as we discussed before, and this enabled us to trim at a different CL. Okay, so it just translates the graph, does not affect the stability, does not change the slope. Now, what does the control surface do? So what happens initially, if this was your initial graph, CM upon CL, you can trim at this CL. If you wanted to trim at this CL, so if you start flying your aircraft at a lower speed, it moves to this CL, right? It moves to this CL. But at that CL, you have a negative moment produced, negative pitching moment, which restores your CL back to this. So when you try to fly the aircraft at a different CL, that is a higher CL means higher angle of attack. So when you fly at lower velocity, that corresponds to a higher CL, that corresponds to a higher angle of attack. When it flies at a higher angle of attack, the aircraft, a statically stable aircraft, produces a restoring CM, that is negative CM, to ensure that you change this increase in angle of attack. It brings it back to the trim. Okay, so that is why we introduced a control surface, that is to counter this stability. To counter the stability, we introduced a control surface. And larger the static margin, we know, is the measure of stability. So larger the static margin, you require more control deflection to control the aircraft. That is analogous to the maneuverability that we had studied. So if it's more stable, it's more difficult to control. Less stable, less difficult to control. Okay. So this is the, this equation gives you how much you need to deflect your elevator such that you can trim at the given CL trim. Okay. So this is the equation where delta E naught is the intercept and this is the slope. The delta E naught is given by this quantity. Okay, CM naught is positive. For CM naught is positive because we just discussed to trim the aircraft at a positive angle of attack. CM delta E we know is negative. We had discussed this again at the beginning of the class. CM delta E is negative and you have a negative sign here. So this entire delta E naught is positive. Here, this term is positive for a stable aircraft. That is the static margin. Static margin is positive for a stable aircraft and CM delta E is negative. So your slope is negative. So your delta E upon a CL trim graph is like this. You have a positive intercept and a negative slope. Okay. So this graph gives you how much you need to deflect your elevator to fly at any given CL trim. Okay. This is CL trim. Now we move on to hinge moment. What is hinge moment? So where is your elevator is located on the horizontal tail at this point. So it rotates about this point, right? So when you deflect your elevator down, it rotates about this point. That is known as the hinge point. The moment about that point is hinge moment. How do you calculate the hinge moment? This is the equation similar to all the other moments, pitching moment, all of them, yawing moment, everything. Half rho v square SE. SE is the surface area of the elevator of this. CE is calculated from the hinge point. Okay, so this is the distance for CE. Okay, convention, that's the convention that we follow. CE is the distance between, is the chord distance between from this hinge point to the tail. CH is the hinge moment coefficient, which we assume to be linearly varying with alpha t, that is the angle of attack at the tail, delta E, that is the control surface deflection, that is elevator deflection, and delta T, which is the trim tab deflection. Okay, so we assume it to be linearly varying with each of these terms. For our simplicity, we assume CH naught to be 0. And for the initial analysis, we also assume that there are no trim tabs. Okay. Now, so when we deflect a stick is the stick control that the pilot has. When he deflects, when he pushes the stick, pushes or pulls the stick is when your elevator deflects. Now, if he continues to hold it there, it's called stick fixed. But if he leaves it, then it's called stick free, or the condition is called floating. So when you deflect it, when it's subject to, suppose this is your tail and this is your elevator. When it's subject to an angle of attack and when your stick is not fixed, what happens? This elevator deflects, it's free to deflect of its own, right? It's not fixed at the hinge point. So that is known as float. Float is when your hinge moment coefficient, CH naught is 0. So equating this to 0, you can find out the delta E float. So the delta E at CH equal to 0 is the delta E float, which is given by this equation, right? Now your CH alpha T and CH delta E. How do you what are the signs of CH alpha T and CH delta E? So when you subject it to a positive angle of attack, when you subject the tail to a positive angle of attack, what moment does it produce at the hinge? When there is a positive angle of attack, your tail deflects towards the top, right? It just floats towards the top, right? Your elevator. Am I right? So even this cross section, you have a center of pressure here. Center of pressure is where we assume all of the aerodynamic forces to be acting. And this is the hinge point. So the force produced here produces a nose down moment, right? About this hinge. So the pitching moment, when it's subject to a positive alpha T, when you assume this to be not deflected, when you assume the elevator to be not deflected, when it's subject to a positive angle of attack at the tail, it produces a lift here. So there's a delta L produced at the center of pressure of the elevator, which produces a nose down moment. So for positive alpha T, you have negative CH. Similarly, when you deflect the elevator down, there is an increase in lift here, right? Again, that acts at the center of pressure, and the moment at the hinge, this is hinge, moment at the hinge would be again nose down. So again, for a positive delta E, deflection of elevator down is considered positive. So for a positive delta E, you have negative pitching moment produced. So both of these derivatives, CH alpha T, CH delta E, are negative. So this term is positive and this entire thing is negative, okay? So this is negative. So for a positive encountering of angle of attack at tail, your delta E float would be negative, okay? Now, if we don't want the delta E to float, what do we do? If this delta E float has to be 0, if your delta E float has to be 0, that is a no float condition, you have to make your CH alpha tail 0. How do we do that? There are two ways that we usually do. There are several ways, but these are two ways that I'll discuss in the lectures. The center of pressure and the hinge have to be at the same point. So if your hinge and center of pressure are at the same point, you will not produce any moment at the hinge, right? When your lift, there is a change in the lift, there won't be any moment produced at the hinge. So your CH alpha tail will be 0. That is one way. Another way is horn balance. So what sir had shown in the actual aircraft. So you have your control surface like this. You have your tail like this. And your elevator is this entire thing. Okay. So when you deflect this portion down, when you deflect it down, that is when you deflect this portion down, this area contributes towards. Am I audible? Can someone confirm if I'm audible? Can you hear me? Okay. So when you deflect this elevator down, this portion contributes towards, if you deflect it down, if there's a positive lift produced, and it produces a negative hinge moment. But this portion, that is towards the leading edge of your tail, that portion produces the reverse moment. So that CP would be somewhere here, only towards the edges, and would produce a restoring moment. So that is another way to cancel the effects of the elevator deflection down, which makes your CH alpha tail 0. Okay, that's called horn balance. Now we discussed these two, CH alpha tail and CH delta E, to be negative. CH delta T, that is the pitching moment produced by the trim tab, that is also less than 0. So what is the trim tab? This is your tail. When you're deflecting the elevator, it floats on top, and you have another, bear with my drawing. Okay, so it produces, now this is the delta E float. This is your elevator, this is your trim tab. So when this is floating above, your trim tab is deflected down and it produces a positive N, which again produces a negative moment about your hinge. So for positive delta trim tab, okay, delta T is delta trim tab, positive delta trim produces negative CH, negative hinge moment. Okay, so all these three parameters are negative. Now, stick convention. So the convention that we follow is pushing a stick forward. What it does is it deflects your elevator down. Okay, so pushing a stick forward means you get more velocity. More velocity means less CL. To ensure that it is in equilibrium, your lift should equal weight, and since weight is not changing, you need to counter the increase in velocity. So you need to reduce your CL. More velocity means less CL. How do you get less CL? You reduce your angle of attack. How do you reduce your angle of attack? You deflect your elevator down. So pushing your stick forward corresponds to deflection of elevator down. Okay, and the reverse. So pulling your stick forward would correspond to deflection of elevator above. This is positive. Okay, delta E down is positive. Now, stick force. So prior to jumping into this, we need to know that the delta E required, this formula, where is this formula? Delta E required to trim the aircraft. This formula depends on this quantity, right? This quantity, and that is for a stick fixed case. Irrespective of what the question says or what we need to find out, this delta E trim, how much we need to deflect the elevator to fly at a given CL, depends on the static margin, the DCM by DCL of a stick fixed case. Okay, this neutral point is for stick fixed case. So we need to remember that. So delta E required is governed by stick fixed static margin, stick fixed neutral point. Okay. Okay. So now we see three cases. So if you're allowing the stick to be not fixed, if your stick free case, you have a delta E float. So when it encounters a positive alpha tail or anything, your delta E floats, your elevator floats. Now, if your floating angle is same as the delta E required to fly at a given CL trim, then the pilot need not apply any force on the aircraft. It is already, the elevator is already deflected to the value that allows us to fly at the given CL trim. Okay, this is case number one. If your delta E float is the same as the one that you require. If it is less than the one that you require, you need to deflect the elevator up, right? So if your delta E float is say 1 degree and the required is 3 degrees, you need to deflect it by 2 degrees more. Positive means you deflect the elevator up, right? So it is already deflected by delta E float. The pilot needs to apply only the additional force required. Okay, so he needs to apply a force that is analogous to 2 degrees change. Okay, only to the difference. When you deflect the elevator up, what was it considered? It is pulling the stick. Pulling the stick is what? Negative. So this is considered positive. Let me just stick forward is positive. Stick pulling is negative. So when you have to deflect the elevator above, you need to pull your stick. When you pull your stick, the force required is negative. This condition, when this is encountered in an aircraft, it's known as stick free stable. When the reverse is encountered, that is your floating elevator angle is more than the one that you require. So he has to reduce the angle. He needs to push. He needs to reduce the angle as in he needs to deflect the elevator down. So he needs to push the stick, right? So this thing is positive. Force required is positive because you're pushing it. Then your elevator comes down. That is considered unstable. So where your floating angle is more than the one that you require, it's considered unstable. If it's less, it's considered stable. And if it's same as the one that's required, it's considered neutrally stable, where the pilot doesn't have to put in any effort to trim the aircraft at his required CL. Okay, now stick force, this is the equation that we follow. HM is hinge moment. Delta E, we know what delta E is. Delta S is the, so, okay, how do I tell you that? So this was your stick, right? Imagine this was your stick. Now how much he pushes it? Suppose he pushes it by this much, and this is the length of the stick. So LS is the length of the stick, which is this much. And how much it deflects, that is delta S, okay? Delta E is a deflection of elevator, HM is hinge moment. So this is what defines your force, stick force. And the force required to be applied by the pilot is the negative of this. Okay, this is the force that is produced. How much he has to apply is the negative of this. Okay, to deflect the elevator. Now we see the differences between the stick free and stick fixed case. What are the differences? The main difference, the only difference in fact comes from the CL tail. So what is the equation for CL tail? Again, assuming linear variation, it depends, it linearly varies with alpha tail and delta E. Now, if it is free, if it's stick free case, this delta E would be what? Delta E float. Substituting delta E float here gives us the final value. CL tail is CL alpha tail into alpha tail. Okay. Now the CL alpha tail is this quantity. So CL alpha tail prime is for a stick free case. This is for free. Is what? Is 1 minus tau CH delta alpha tail and CH delta E into your original CL alpha tail. Okay, what does this say? This quantity is negative, this quantity is negative, we have seen. Your tau, control surface effectiveness parameter, is positive but less than 1. So this entire term would be less than 1, and what it tells us is CL alpha tail prime, that is for a stick free case, this is for fixed, is less than your CL alpha tail. Okay, this is stick free, this is stick fixed. Okay. So this is the equation that relates the two neutral points, the stick fixed neutral point and the stick free neutral point. So this is the equation that relates these two neutral points. Okay, where VH is the horizontal tail volume ratio, eta is the horizontal tail efficiency factor, CL alpha tail is for the fixed case, CL alpha wing we know. This is the downwash component, tau is control surface effectiveness parameter, and these are the two derivatives that we just saw, both with negative sign. Okay. Now, doing some manipulations on this equation, we can also relate the static margins of these two cases, stick free case and stick fixed case. For a statically stable aircraft, this value is negative. We need DCM upon DCL to be negative, right? So your static margin should be positive. For static margin is minus DCM upon DCL. So we need this quantity to be negative for a stable aircraft. This quantity is negative. Now let's look into this quantity. This is negative, this entire thing becomes positive. Tau is positive. This is a positive quantity less than 1. CL alpha tail is positive, CL alpha wing is positive, these two are positive. So this entire term is positive. So what it does is it destabilizes, it contributes towards destabilizing. It's destabilizing the stick fixed case. This was negative and you're adding a positive quantity to it. So your DCM upon DCL free. So DCM upon DCL prime is less stable than the fixed case. Okay. CM by DCL fixed. Your DCM upon DCL for the stick free case is less stable than DCM upon DCL fixed because of this positive destabilizing term. Okay. Now this is just a comparison between the two cases, stick fixed and stick free. So first we look into the pitching moment at the CG. Pitching moment at the CG, this is the equation that we know, where here the only difference is DCM upon DCL fixed. Here is DCM upon DCL free. CM naught would also vary, but we'll look into that in the next stage. Okay. So these are the points of variation for pitching moment. Next is CM naught. CM naught equation for stick free case, we know this is the contribution of the wing, this is the contribution of the fuselage, and this is the contribution of the tail. The only point of variance between stick fixed and stick free we saw was that the CL alpha tail changes. So that's the only point of variation here. It becomes CL alpha tail prime, which is less than the CL alpha tail for stick free case. Similarly, we see how DCM upon DCL varies. This is the equation for DCM upon DCL. Should be a bar. Okay, should be a bar. It's non-dimensional. So we can see that this is the equation that we know for DCM upon DCL, the negative value. The only point of variance here again is CL alpha tail. Again, the neutral point. Same thing for the neutral point, only the CL alpha tail changes. Okay. Now let's look into a few questions. In the figure given below, which aircraft will have higher stability margin? Think about it and let me know. Someone please tell me this answer. Just look at the graph, look at the two. So the dark line, the solid line represents aircraft A, the dotted line represents aircraft B, and it's plotted. Each of those aircraft, the graph is plotted for different CG values. Yeah. Okay, one is at 0.25 C, and one is at 0.35 C. Okay. So just tell me which aircraft would be more stable. Stability, what is the criteria? What is the criteria for longitudinal stability? We discussed this right at the beginning of this tutorial. Can you hear me? Can you hear me? Can someone just confirm if you can hear me? DCM upon DCL should be less than 0. Yes. So condition for stability, static longitudinal stability is DCM upon dou CL should be less than 0. So your static margin is minus dou CM upon dou CL. Okay. So higher the static margin, higher is your stability. So higher is the slope, and the magnitude of the slope, greater is the magnitude of the slope, greater is your stability. So what it means is the slope of your graph, the slope between CM versus CL should be higher, right? More stability means more slope, right? More stability corresponds to more slope. So which of these aircrafts have more slope? Just take any line. So just take this first line, 0.25.
Aircraft B.
Aircraft B has higher slope. Correct. He's right. Okay. B. Okay. Now next question. Which airplane has more control power? What is control power? What was control power for the longitudinal case where the control surface is elevator? What was control power? CM delta E. Correct. So which of these aircrafts have a higher CM delta E? CM delta E is your control power. Which of these aircraft, this or this, which has a higher CM delta E? So let's calculate for aircraft A. Okay. CM, we'll take it at this point. Okay. Change in CM is 0.1. And how much is the change in elevator deflection? 10 minus 0. Okay. That is 10. This is the first slope. What is this value? You listening to me? Okay. So B aircraft, your slope, so DCM is what? You have 0.4 minus 0.2. 0.4 minus 0.2 by a change in elevator is the same. This is 0.2 by 10, which is 0.02. This is higher, right? So aircraft B has more control power. This is CM delta E by 2. For aircraft A, it is 0.01 and aircraft B, it is 0.02. So aircraft B has more control power. Okay? When an aircraft trim speed is changed from 60 meter per second to 100 meter per second, maintaining the same altitude, will the elevator float more or will it float less? Think about it and tell me. Elevator float, delta E float. Look into that formula and think about it. When the trim, yes. Was somebody saying
less?
Less, okay. Can somebody else say something? Okay, let me just go over this. So when you increase your velocity, more velocity means less CL. Less CL means, how do you ensure less CL? You get less angle of attack at tail, okay? How do you get a less angle of attack at tail? You deflect your elevator down, okay? That we know. Now, this is the formula for delta E float. So initially your alpha T, suppose it was 2 degrees. Now, when you want to change it from 60 to 100, so alpha T1, imagine it was 2 degrees, and alpha T2, it has to be less, right? For more velocity, less CL, less alpha T. Imagine it was 1 degree. I'm just taking random values, but to show the variation. So delta E float in this case, float 1 would be greater than delta E float 2 or less than? Imagine these both as 1. So your delta E float would be minus 2. And here this would be minus 1, right? The magnitude would be lesser. That is true. So you deflect your elevator, it floats less. So the elevator deflection would be less for when your aircraft is changed, when it's trimmed at a higher velocity. Okay, she's right. Less. Okay. To reduce the floating tendency of an elevator, hinge line has to be moved aft or forward. So your tail is here. This is your elevator. This is your hinge line. So should this hinge line be moved aft or forward to reduce the floating tendency of an elevator? We just discussed the no float case, right? So that one of the things that I told was to move the hinge point, one of the ways to accomplish that. So in this case, to reduce the floating tendency of an elevator, should this hinge line, this is just a cross section. So hinge line, should it be moved aft or forward? What contributes towards the floating? This is the center of pressure, and this moment contributes towards floating. If you want to reduce this floating tendency, you need to reduce this moment. How do you reduce this moment? You have no effect, a control over the lift produced. You have no control over the force produced at given angle of attack, right? So how do you reduce this?
After you move it.
Sorry?
After you move it.
Yes. After is the right answer. So these are a few questions that most of them I think are from your current assignment. So I will not be giving you answers, but we'll just go over that. Stick fixed and stick free. One second. Stick fixed and stick free, neutral point or whatever, they are similar. They are similar in the sense that both of them, so if you consider neutral point, it's when DCM upon DCL is 0. Okay. 0. For neutral point of stick free case, DCM upon DCL prime is 0. That way it's similar, but they are two different cases, right? One is when you fix the stick and one is when you leave the stick free. False, they are not similar. Okay. Next, which of the following is correct for hinge moment? I think this is one of your assignment questions, so we will not be discussing the answer, but I'll just give you a hint. Which one of the following is correct about hinge moment? So just look at the hinge moment formula and you will be able to get the right answer, right? Right? Okay. Next, stick force is a function of. Stick force is a function of. Should be lifting, I think. Again, look into the formula for stick force. We had just discussed this in the first slide for week 6. Stick force depends upon hinge moment, delta E, LS, delta S. Okay. Again, this I think is a question from your assignment, so I will not be telling you the answer, but this is the formula. This is a hint with which you can solve it. So this is the question. For airplane in pull-up maneuver, the following expression was obtained. Okay. Something wrong. Just a minute. There seems to be something wrong with the pen. Okay, so this is your equation that is given, dFS by dN for pull-up, and this is dCm by dCl, stick free case. So this is the equation that was obtained by a student for the CG location is given to you, and stick free, stick fixed and stick free static stability are given to you. The first question is find the stick free maneuver point. NM dash is the stick free maneuver point. How do you find that? So you have a static margin. How do you find them? And you have the CG. Okay, so these are the two equations that so you have, this is for a stick fixed case. Okay, that's not what's asked, but let's just go over that. For a stick fixed case, what is the static margin? Stability margin is 0.25. 0.25 is equal to x bar np. so this nm dash, we are just using this notation, they are using that notation. Okay, nm is nothing but x bar np, and nm prime is nothing but x bar np prime. So x bar np minus x bar cg. That is what x bar np is what we need to find out. Minus x bar cg is, what is the value for C, what is the cg location? 0.3. Okay. Okay. So your stick fixed neutral point is 0.55, but they've asked you for stick free maneuver point. This is the equation for maneuver point. So when you're maneuvering, you just call it a maneuver point. It's analogous to the neutral point. Okay. So for your stick free case, what is the stability margin? 0.2. And you have x bar mp minus x bar cg. So your x bar mp prime is cg is same, 0.3 plus 0.2. So you get 0.5, right? Okay, this is the neutral point, okay? So stick free neutral point is 0.5, okay? Okay, so now they've asked you to find out this is my bad, this is not the same thing, this is wrong, this is not the same. So we have found out the neutral point, we need to find out the maneuver point now, okay? I made a mistake there, it's not the same. Nm prime is the stick free maneuver point. So what is how do you define maneuver point? Delta E, d delta E upon dn is 0. The point at which this value becomes 0, this slope becomes 0 is defined as the maneuver point, right? Or recall this from the previous, I think, week 5 content, week 4 content. Now how do you deflect the elevator? You deflect it by giving the control force. So this is also analogous to dfs by dn. So when d delta E by dn is 0, dfs by dn is also 0, right? Right. So substitute the values here to find out the maneuver point. So that equation is dfs by dn is 0 is equal to 120 into dcm upon dcl free minus 12. What is dcm upon dcl? It's a stability margin, right? It's a minus of the stability margin. So that is x bar cg minus x bar np prime minus 12. Now, what is maneuver point? Maneuver point is the CG location at which dfs by dn equal to 0. Okay, so we need to find out this CG location. So 0 equal to 120 into x bar CG minus x bar np is 0.5 minus 12. Can somebody calculate the value of x bar CG from this equation? Just calculate the value. 12 divided by 120 plus 0.5, right? 0.6. So here you get x bar CG as 0.6. So x bar CG at which your dfs by dn is 0 is nothing but your x bar maneuver point. Okay, 0.6 is the answer. Is this clear? Okay, I'm just going to go ahead. Okay. Find the CG limits permitted if the magnitude of stick force per G. Magnitude of stick force per G is this. This is nothing but dfs by dn, okay? Is to remain within 10 and 30. It's the magnitude, they have not mentioned the signs. So now what we do is we plug in these values, these 10 and 30 values into this equation to find out the limits of CG. So what was our equation? dfs by dn is equal to 120 x bar cg minus x bar np prime minus 12. So for the first case we take 10, okay? 10 equal to 120 x bar cg minus x bar np was np prime. Stick free neutral point was 0.5. 0.5 minus 12. In this case, what is your x bar CG? CG. Just calculate this value. Can you calculate that value and tell me what is CG? 0.6833. Now, case number 2 is when you take 30, you take the next limit. It is 120 x bar CG. All the other parameters remain same, only your DFS by DN changes, okay? In this case, what is your x bar CG? Calculate this, just one value, just calculate it. What is the value here? Am I audible? 0.85, yes. 0.85. Now the next case, they have said magnitude of stick force per G. So if you push it, it's positive. If you pull it, it's negative. We have considered only the pushing cases. Now let's consider the pulling cases. So that is minus 10 is equal to 120 x bar CG minus 0.5 minus 12. Here, what is x bar CG? .516. Okay. Now the next case, final case is minus 30. Is 120 x bar CG minus 0.5 minus 12. In this case, x bar CG is 120 minus 12. 0.35, right? Correct me if I'm wrong somewhere, okay? 0.35. So they've asked you find the CG limits permitted if the magnitude of stick force is between 10 and 30. Ideally, they should have given two values, the lower and the upper limit, but let's see which of these values are given the options. So the lower limit is given. So the limits of the CG for the stick force to remain within magnitude of 10 and 30 are 0.35 and maximum 0.85. Okay, so 0.35 is what is given in the options. So that is the right answer. Ideally, they should have given two. When they ask you for limits, they give two values. Okay. I hope this is clear. Can I move on? So this is another one question that's given in your assignment. So we won't be solving it, but I'll just give you the equation. So what they've given is the hinge moment characteristics. So you have those three coefficients, those three derivatives. So you have CH alpha tail, CH delta E, CH delta tail, delta trim tab. So alpha tail is angle of attack at tail, delta E is elevator deflection, delta T is trim tab deflection. You have the three derivatives and you have two angles. They've asked you to find out the stick free elevator deflection. That is nothing but delta E float. For delta E float, what do we do? CH is 0. For float, equal to free, what it is CH is 0. So you take CH equation, equate it to 0, find out delta free. CH equation is this. We can find out the delta. Hinge moment coefficient depends upon, again, we know this equation. Just look at this equation and you will be able to answer this, what it depends on, right? We just discussed what each of these alpha tail, delta E, delta T represent. Next, this again is a question that is given there. So we have just discussed the formula for stick force in terms of hinge moment, right? So stick force in terms of hinge moment, this was the formula. You should be able to solve this from here. So with this, we end today's tutorial. I hope everything was clear. Does anyone have any questions?
1 minute, madam. One question I asked regarding. Hello, can you able to hear?
Yeah, I can hear you. Continue.
1 minute. 1 minute. 1 minute. Regarding this one, that aircraft is flying in the south direction at velocity 50 meters per second and crosswind from west to east. Slide slip angle actually minus 3.433. It was written accepted, but it will be plus 3.433.
Were you there from the beginning of this tutorial?
Just for a few minutes. I was out. That's what.
Yeah, I had mentioned, and I think Mr. Prashant, the other TA, has responded to your mail saying it would be resolved, right?
No, I have not got a mail.
He has responded to your mail saying it will be resolved.
Okay, then I will.
And
And
I
madam-
also mentioned that this is wrong, and I've marked the correct answer. It will be resolved.
Okay. I was just out.
Yeah. So
Okay.
I had mentioned, okay, at the beginning.
And this one, assignment 2 and assignment 3 question 2, that both answer were correct, means 0.15.
Again, Mr. Prashant has responded to your mail saying it will be resolved.
Okay, I will check it up, but I have not received. Okay, I will check it up once again, or I will send. Okay, madam.
Yeah.
Thank you.
What was the suggestion, Eric?
Hello, madam. How are you?
I'm good.
So now, me, I'm from Africa, but you are fast in speaking, and sometimes your English is very difficult for me to understand or to catch up. So could you please next time to go slowly so that I could follow?
You're asking me to go slow, right? You want me to go slower, right?
Yeah, but not slow as slow, but slow so that I could understand.
Okay, so I should speak slowly. I get it. I will look at that.
Yeah.
Thank you for
Thank
that.
you.
I will try going slow next
Okay,
time.
thank you, madam. Thank you.
Okay.
Anybody has anything else?
Thank you, madam.
So if there are no further questions, we'll end it here. We'll meet again next week. Thank you.